Welcome to the deep dive. Today we're tackling a topic that's absolutely foundational in organic chemistry.
Definitely.
But it often feels, a bit like trying to visualize something invisible while juggling molecular configurations.
Right. The 3D shape of molecules.
Exactly. We're diving into Chapter 7 of Organic Chemistry as a Second Language. Our mission today is basically to unlock that 3D code, making sense of R, S, and enantiomers, meso compounds, all that stuff. We want to give you the tools to really see these things in 3 dimensions.
And this is really where organic chemistry gets fascinating, I think. Understanding configurations isn't just like putting a label on something. It's fundamental to how molecules recognize each other.
Right.
Think about drugs, pharmaceuticals. Their effectiveness, sometimes even their safety, can completely depend on whether it's the R or the S version.
Right, I've heard about that.
Yeah, one configuration might be the cure. Its mirror image could be useless or worse, actually harmful. The thalidomide story is a classic tragic example. One enantiomer helped, the other caused terrible birth defects.
Oh.
So this chapter helps us get a handle on that essential handedness of molecules.
And the book uses a great analogy right at the start to help grasp handedness, our own hands. How does that help clarify things?
It's perfect, really. Because your right hand is always your right hand. Doesn't matter how you turn it or twist it or put it behind your back. You can't just manipulate it so it suddenly becomes a left hand. That basic right-handedness, that's its configuration. It's a fixed 3D arrangement. And this immediately highlights a really crucial distinction, one that trips up a lot of students: the difference between conformation and configuration.
Right. Conformation versus configuration.
Exactly. Conformations are like all the different ways you can twist your hand or fingers. They change easily, usually just by rotating around single bonds, like temporary shapes. But configuration, that's like whether it's right or left hand in the first place. It's inherent. It's the molecule's specific R or S label, and it only changes if you break and make bonds, through a chemical reaction.
Okay, so conformations are flexible shapes. Configurations are fixed identities.
You got it. A molecule might wiggle through many conformations, but its configuration stays the same unless a reaction happens.
So if this handedness, this configuration is so important, where do we even start looking for it in a molecule? What are we actually identifying?
We're looking for specific points of handedness called stereocenters. You'll also hear them called chiral centers. Same thing, really.
Stereocenters, okay.
Fundamentally, it's usually a carbon atom that's bonded to 4 completely different groups.
4 different groups.
Yes, and this is key. It's the entire group that matters, not just the atom directly attached. That's a common slip-up.
How so?
Well, you might have a carbon bonded to, say, a methyl group, CH3, an ethyl group, CH2, CH3, a bromine atom, and a hydrogen atom. All 4 of those entire things are different. So that carbon is a stereocenter.
Got it. Different groups, not just different atoms right next door.
Precisely. And for a quick check, look for symmetry. If a carbon has 2 identical groups attached, like a CH2, which has 2 hydrogens, or maybe it's bonded to 2 methyl groups.
It can't be a stereocenter.
Right. It's automatically out. Same idea in rings. If you trace around the ring one way from a carbon and trace the other way, and the path is identical.
No stereocenter there either.
Exactly. You need that fundamental asymmetry.
That's helpful. And you mentioned drawings sometimes don't show the 3D wedges and dashes. What does that usually mean for a stereocenter?
Good point. If you see a reaction product, for instance, and there's a known stereocenter but no dashes or wedges drawn, it often implies you've got a racemic mixture, meaning an equal 50-50 mix of both possible configurations, both the R and the S forms. Their properties often cancel out in some ways. It's chemical shorthand.
Right.
And all these molecules, same formula, same connections, but different 3D shapes, they fall into the big umbrella of stereoisomers.
Okay.
And within that category, the specific pairs that are non-superimposable mirror images, like your hands, those are called enantiomers.
The mirror image pairs.
Yes. They are exactly mirror images, but you just can't stack one perfectly on top of the other.
And I guess it gets more complicated if there's more than one stereocenter.
Oh, absolutely. If you have 2 stereocenters, suddenly you have potentially 4 possibilities. You could have R, RS, or SR, SR, or SS.
Wow, okay, so it multiplies quickly.
It does. That's why being able to identify them and then label them correctly with R or S is so crucial.
All right, so let's get into that labeling. We found a stereocenter. How do we assign its specific configuration? How do we figure out if it's R or S?
Okay, it's a solid 2-step process. Step 1 is all about assigning priorities. You give each of the 4 groups attached to the stereocenter a rank, from 1 highest down to 4 lowest.
Priorities 1 to 4? How?
The main rule, and usually the easiest, is atomic number. You look at the atom directly attached to the stereocenter. The higher its atomic number, the higher its priority.
Simple enough. So oxygen beats carbon.
Yep. And bromine beats chlorine, which beats fluorine, which beats oxygen, then nitrogen, then carbon. You just need to know the relative order of common atoms. CNO, FPS, Cl, Bri. Those cover most cases.
And hydrogen?
Hydrogen, if it's there, is almost always going to be your lowest priority, number 4, because it has the lowest atomic number. Now, the slightly tricky part comes when you have a tie. Let's say the stereocenter is bonded to 2 carbons.
Right. Same atomic number. What then?
This is where people sometimes make a mistake. You don't add up atomic numbers down the chain. Instead, you move outward along each chain simultaneously, atom by atom, until you find the first point of difference.
First point of difference, like a tiebreaker.
Exactly. Imagine one chain is carbon-hydrogen, and the other is carbon-oxygen-carbon. You compare the first carbon's tie. Then you compare the next atoms attached to those first carbons. One pad has another carbon, the other has an oxygen.
Oxygen wins, higher atomic number.
Right. The CO path gets higher priority than the CC path, regardless of what else is further down the chains. You stop at that first difference.
Okay, that makes sense. Don't add, just compare outwards. What about double or triple bonds?
Special rule there. You treat multiple bonds as if the atom is bonded to multiple phantom atoms. So a carbon double bonded to an oxygen, CO, is treated for priority purposes as if that carbon is bonded to 2 oxygens. A carbon triple bonded to a nitrogen is treated like it's bonded to 3 nitrogens.
Okay, so double counts as 2, triple is 3.
Basically, yes. It helps break ties when you have those multiple bonds involved.
Yeah.
So once you've got your priorities ranked 1, 2, 3, 4, that's step 1 done. Step 2 is actually determining R or S.
The final verdict.
Yeah. And the ideal situation, the easy one, is when your lowest priority group, number 4, is pointing away from you. In drawings, that's usually shown with a dashed line.
Okay, if a 4 is on a dash.
Then you just ignore the 4 for a second and trace a curve from priority 1 to 2 to 3. If your finger moves clockwise, like turning a steering wheel right, the configuration is R for rectus, Latin for right.
R for right turn, clockwise.
And if tracing 1 to 2 to 3 goes counterclockwise, like turning the wheel left, it's S for sinister, Latin for left.
S for counterclockwise. Got it. But what if number 4 isn't on a dash? That seems like the tricky part.
That is where it gets trickier,
Yeah.
and where visualizing in 3D really helps but can also be tough. Ideally, if 4 isn't on a dash, you'd mentally rotate the molecule in your head until the number 4 group is pointing away from you.
Mentally rotate. Easier said than done sometimes.
It really is. The book uses a neat analogy. Imagine sticking a pencil through the molecule, spearing the number 4 group, and using that as an axis to rotate everything else till 4 points back. Then you trace 1, 2, 3 on the remaining groups. But for those of us, myself included sometimes, who find that mental gymnastics a bit much, especially under pressure.
Yeah. Is there a shortcut?
There's this, a very reliable trick. First, assign your priorities 1, 2, 3, 4 as usual. Now, if 4 is not on the dash, maybe it's on a wedge coming out at you or even in the plane, find the group that is on the dash. You perform a single imaginary swap between the number 4 group and whatever group is on the dash. Just switch their positions in your mind or on your paper.
Swap 4 with the dashed group.
Right. Now, the number 4 group is on the dash in this temporary swapped version. So you determine the configuration of this swapped molecule, trace 1, 2, 3, see if it's R or S.
Okay.
And here's the crucial last step, the part people forget. Because you did one swap, you inverted the stereocenters configuration. So the actual configuration of your original unswapped molecule is the opposite of what you just found for the swapped one.
Ah, so if the swapped version looks like S, the real one is R.
Exactly. And if the swapped looks R, the real one is S. It's a fantastic way to get the right answer without having to do complex mental rotations. Just remember that final flip.
Okay, that swap trick sounds really useful. So once we've confidently assigned R or S to all the stereocenters, how do we actually, put that into the molecule's official name?
It integrates pretty smoothly into standard IUPAC nomenclature. If your molecule only has one stereocenter, you just put R or S in parentheses right at the beginning of the name.
Like R-butan-2-ol or something?
Precisely, R2-butanol, yep. If you have multiple stereocenters, you need to say which configuration belongs to which center using number locants.
Ah, so you need the address for each R or S.
Exactly. So you might have a name like 3R4S, 3,4-dimethylhexane-2,1. That tells you the stereocenter at carbon 3 is R and the one at carbon 4 is S.
Got it. Numbers indicate position, RS indicates configuration, and you italicize that part.
Yep. The 3R4S part is typically italicized in the formal name.
Okay. Now, we've focused on stereocenters, but you mentioned earlier that just using cis and trans for double bonds isn't always enough, right?
That's right. Cis-trans works fine if you have, say, two identical groups on the double bond carbons to compare, like cis-2-butene versus trans-2-butene. But what if all four groups attached to the double bond carbons are different?
Then cis-trans doesn't apply.
Exactly. That's why we have the easy nomenclature. It's more general, more powerful. It works for any double bond.
E and Z. Okay, how does that work? Is it similar to RS?
It uses the exact same priority rules we just discussed for RS. Atomic number, first point of difference, treating double triple bonds as multiple single bonds.
Yeah.
All that.
Okay, so we assign priorities again.
Yes. But this time, you look at the two groups on one carbon of the double bond and decide which has higher priority. Then you do the same for the other carbon of the double bond.
So find the higher priority group on each side of the double bond.
Correct. Once you've identified the higher priority group on the left carbon and the higher priority group on the right carbon, you look at their relative positions. If the two higher priority groups are on the same side of the double bond, both pointing up or both pointing down relative to the double bond axis, we call it Z.
Z4.
Z comes from the German word zusammen, which means together. So high priority groups together.
Okay. Z is samizeit. Got it.
Huh. Nice mnemonic. And if the two higher priority groups are on opposite sides of the double bond, one up, one down, we call it E.
And E is 4.
E comes from entignen, German for opposite. High priority groups opposite E.
E for opposite. Okay, I can remember that. And how does that go in the name?
Very similar to RS. It goes at the beginning, usually with a number indicating the position of the double bond. So you might see something like 3Zs 5S, 4-fluoro-375, dimethylheps-3-ene.
Wow, packing a lot of info in there. Z for the double bond at position 3, S for the stereocenter at position 5.
Exactly. It gives a complete picture of the molecule's stereochemistry.
All right, we know how to find stereocenters, label them RS, and handle double bonds with EZ. Now let's zoom out a bit and talk about the relationships between different stereoisomers. We mentioned enantiomers.
Right, the non-superimposable mirror images always come in pairs.
How do you actually draw the enantiomer of a molecule you're given?
Well, the simplest way, if you have a standard dash wedge drawing, is just to invert every stereocenter. Change all the dashes to wedges and all the wedges to dashes. That physically creates the mirror image.
Swap all dashes and wedges. Okay.
But sometimes, especially with rings like cyclohexane chairs or bicyclic systems, you don't always have explicit dashes and wedges. The 3D shape is implied.
Right.
In those cases, a really useful technique is to imagine putting a mirror right next to the molecule and drawing what you'd see in the reflection.
The mirror on the side method.
Exactly. It often works much better for those implied 3D structures than trying to redraw everything with dashes and wedges first.
Okay, so enantiomers are perfect, non-superimposable mirror images. What about diastereomers? How do they relate?
Diastereomers are basically any stereoisomers that are not enantiomers, meaning they have the same connectivity, they differ in 3D space, but they are not mirror images of each other.
Not mirror images. So how do they differ from enantiomers?
The key difference usually arises when you have multiple stereocenters. For enantiomers, all stereocenters are inverted. R becomes S, S becomes R. For diastereomers, some but not all of the stereocenters are different.
Ah, okay. So if you have an RR molecule, its enantiomer is SS. But the RS and SR versions would be diastereomers of R and also diastereomers of SS.
Precisely. And the RS and SR are enantiomers of each other. It's like a family of isomers. Enantiomers are always just pairs within that family, while diastereomers represent all the other non-mirror image relationships.
And you mentioned easy isomers before.
Right. Easy isomers are actually a specific type of diastereomer. They are stereoisomers, different spatial arrangement around the double bond, but they certainly aren't mirror images of each other, so they fit the diastereomer definition.
Okay, so the stereoisomer family can have pairs of enantiomers and then multiple diastereomeric relationships between the non-enantiomeric pairs.
You've got it. Enantiomers are pairs, diastereomers cover the rest. Now this leads to a really interesting and sometimes confusing situation. What happens if a molecule actually is superimposable on its own mirror image, even though it contains stereocenters?
Wait, how can that happen? If it has stereocenters, shouldn't it be chiral? Shouldn't it have a non-superimposable mirror image?
You'd think so, but no. This is the special case called a meso compound. It's a molecule that has stereocenters, usually 2 or more, but the molecule as a whole is achiral because it's superimposable on its mirror image.
So it doesn't have an enantiomer.
Exactly. It is its own mirror image, effectively. The source book uses a nice analogy. It's like a molecule born about a twin. This means that if you have a family of potential stereoisomers based on the number of stereocenters, say, you expect 4, but one is meso, then you only actually have 3 distinct stereoisomers, the meso compound and 1 pair of enantiomers.
Okay, that's weird but important. How do you spot a meso compound?
The most common way, the thing to look for first, is an internal plane of symmetry. Imagine slicing the molecule in half with a mirror plane. If one half is the perfect reflection of the other half, then the molecule is meso.
A mirror plane within the molecule?
Yes. Think about cis-152 dimethylcyclohexane in its chair form, or even drawn flat. You can draw a plane right through the middle of the ring, bisecting the bond between carbons 1 and 2 and the bond opposite it. The methyl group on one side reflects onto the methyl group on the other, same for the hydrogens. That internal symmetry makes it meso, even though carbons 1 and 2 are technically stereocenters.
Ah, the symmetry cancels out the chirality.
Precisely. There's also another, less common type of symmetry called a center of inversion that can lead to a meso compound, but the internal plane is the main one to watch for. But the absolute guaranteed fail-safe way to check if something is meso. Draw what you think is its enantiomer by inverting all stereocenters or using the mirror method. Then try to rotate that enantiomer in space to see if you can make it perfectly overlap with the original molecule.
If you can superimpose the mirror image onto the original,
then it's not actually an enantiomer, it's the same molecule. And therefore, the original molecule must be meso. This test always works, even if spotting the symmetry plane is tricky.
Okay, meso compounds are definitely something to watch out for. Now, I know there's another way chemists draw these molecules, especially long chains with lots of stereocenters. That looks completely different.
Ah, yes, you must mean Fischer projections.
That's the one. Looks like a cross, or lots of crosses stacked up.
Exactly. They're a very useful shorthand, especially for things like sugars, carbohydrates, which often have many stereocenters in a row. It saves drawing loads of dashes and wedges.
So how do you interpret those lines? What do they mean in 3D?
There's a strict convention you have to remember. All the horizontal lines in a Fischer projection represent bonds coming out towards you, like wedges.
Horizontal lines or wedges coming out. Okay.
And all the vertical lines represent bonds going away from you, into the page, like dashes.
Vertical lines are dashes going back. Got it. Horizontal out, vertical back.
You absolutely need that rule locked in to make sense of them. The source shows a nice way to visualize it. Imagine the carbon chain bending like a bracelet to put all the substituents on horizontal lines pointing outwards, and then flattening that onto the page.
Okay, so how do you assign RS from a Fischer projection intersection?
You use the exact same rules as before assign priorities 1 to 4. Then, remembering horizontal wedge out and vertical dash back, you determine R or S. Often, the lowest priority group, like H, will be on a horizontal line coming out.
Ah, so you might need the swap tray.
Very often, yes.
Yeah.
If number 4 is horizontal, a wedge, you can do the swap trick. Swap it with whatever group is on a vertical line, a dash, determine R or S for the swap version, and then flip your answer to get the configuration of the original Fischer projection.
Okay, same rules apply. Just have to remember horizontal is out, vertical is back.
Exactly. Now, one major pitfall with Fischer projections, drawing the enantiomer.
How so?
Students are sometimes tempted to just rotate the whole Fischer projection, drawing 90 degrees on the page. Do not do that.
Why not?
Because rotating it 90 degrees would swap which bonds are horizontal and which are vertical, effectively inverting all the stereocenters in a way that doesn't correspond to a simple mirror image. It messes everything up.
Okay, so how do you draw the enantiomer of a Fischer projection?
You treat it like any other drawing where dashes and wedges are implied. Use the mirror on the side method. Just draw the mirror image reflection next to the original Fischer projection. That correctly inverts all the stereocenters and gives you the true enantiomer.
Mirror image, not rotation. Got it.
Okay, there's one last really crucial concept we need to cover from this chapter, and it's a point of major confusion for many students, but vital for lab work. That's optical activity.
Optical activity. Okay, what is that?
It's a physical property that chiral molecules possess. Remember, chiral means handed, so non-superimposable on its mirror image and not meso.
Right, chiral molecules.
These chiral molecules have the ability to rotate the plane of plane polarized light. Imagine light waves vibrating in all directions. A polarizer filters it so it vibrates in only one plane. When this plane polarized light passes through a sample of a chiral compound,
it rotates the plane.
Exactly. The plane of vibration gets twisted, either to the right, clockwise, or to the left, counterclockwise.
And that's measurable.
Yes, using an instrument called a polarimeter. If the compound rotates the light clockwise, we call it dextrorotatory, and use a plus sign. plus in its name. If it rotates counterclockwise, it's levorotatory, and we use a minus sign.
Plus for clockwise, minus for counterclockwise.
Right. And importantly, a racemic mixture, that 50-50 mix of enantiomers we talked about, will be optically inactive. The plus rotation from one enantiomer is perfectly canceled out by the rotation from the other. Meso compounds are also optically inactive because they aren't chiral overall.
Okay. So chirality leads to optical activity, measured as plus or plus. Where's the confusion?
The confusion, the huge misconception, is thinking that the RS configuration is somehow related to the plus optical rotation.
They aren't related.
They are completely unrelated. This is so important. R and S are labels. They are part of a naming convention, a system we invented to describe the absolute 3D arrangement of atoms at a stereocenter.
RS is a label based on structure.
Exactly. Plus and minus, on the other hand, describe a physical property, how the molecule interacts with light. This property must be measured experimentally in the lab.
So you can't predict plus a blank just by looking at R or S.
Absolutely not. You might have an R compound that is plus, or an R compound that is plus. You might have an S compound that is plus, or an S compound that is. There is no correlation.
Wow. Okay, that's a good clarification.
It really is. Optical rotation can even change depending on temperature or the solvent used for the measurement, while the molecule's R or S configuration stays exactly the same. RS is fixed, plus man is experimental.
So on an exam, we'd be expected to figure out R and S.
Yes, definitely. You need to be able to assign RS configuration based on the structure.
But we wouldn't be expected to guess if it's plus or...
Correct. Unless you are given experimental data, like a measured rotation value. You cannot and should not try to predict the sign of rotation from the structure or its RS designation. They are independent concepts.
Well, we have definitely gone deep into the 3D world of molecules today. I feel like this dive has really demystified a lot of that complexity.
I hope so.
We've covered how to spot stereocenters, how to use the RS system to give them a unique label, how to handle EZ for double bonds.
Right, and untangled the relationships in enantiomers as mirror images, diastereomers as the others.
And those tricky meso compounds that look chiral but aren't. Plus, understanding Fischer projections and that crucial difference between RS and optical activity.
And the so what, the reason this all matters so much is that this knowledge is just fundamental. It's not just theory. It dictates how reactions happen, how enzymes grab onto specific molecules, how drugs work or don't work. It's all about that precise 3D fit and recognition. So keep building that intuition for seeing molecules in 3D.
It really makes you think differently.
Definitely. Here's a final thought. Next time you read about a new drug, or even take a medication, pause for a second and consider. Its effectiveness, maybe even its side effects, could very well hinge entirely on whether it's the R or the S molecule they managed to synthesize or isolate.
Such a tiny difference on paper, but huge consequences.
Exactly. A massive real-world impact.
Thank you so much for joining us on this deep dive. We hope this journey through molecular configurations has made things clearer and maybe even, dare I say, a little less intimidating.
Keep practicing those visualizations.
Absolutely. Keep exploring, keep learning, and we'll catch you on the next deep dive.